And this is also a work in progress. With Guzman, Hernandez, Scheffler, who is here. And Matthias Sempe. Well, as everybody here knows, that the goal of this collaboration is to solve confinement and understand dynamics of confining strings. But this talk will be...
Sorry, you have to put on to be recorded.
Is it turned on?
It's on.
Okay,
Yep,
thank you.
Thank you.
So this talk will be about another well-seasoned problem in quantum field theory. Namely, the question is, I start with arbitrary quantum field theory in d dimensions, and there is one set of physical observables which one can calculate, which are related with infinite volume, well, and kind of the most robust set of physical observables here is the S matrix, the scattering amplitudes. On the other hand, one can put theory in a finite volume, which is, well, for me it will be always a torus. Well, it's one cube if I'm thinking about theory in 3D. And so here one can calculate the spectrum of discrete spectrum of finite energy excitations. Well, and we I think there is expectation that there should be exact relation between these two observables, which is non-perturbative, which doesn't depend on the dynamics on the theory, or at least largely doesn't depend on the dynamics of the theory. And understanding this relation, that's the topic of this talk. And of course, many people in the audience understand the reason why this talk is here. And the reason is that well, in recent years, much of the progress in understanding of confining strings was coming from lattice simulations by Mike Andreas, who are here, by Michele, who are here. And for confining strings, what they measure exactly these quantities, but actually for strings, they measure, the bullshit theory is one-dimensional, so they measure the spectrum of excitations of a 1 plus 1 dimensional theory on a circle, and that these measurements led quite a bit of insight into the bullshit dynamics of long strings. And we're reaching the point really where the quality of lattice data is such that where really the further progress in extracting information from this data, the abstraction is really our ability to extract theoretically the information from, because we don't know this relation in general. And for the same reason, this problem was, that's a classic problem which is being usually studied by lattice field theories. So let me give you a summary of kind of my understanding of what is currently understood about this problem. So the status is, so first of all, for arbitrary D and theory with a gap, which is gapped, so there is a mass gap in the bulk. Then for states below 3 particle threshold, there are so-called Lucia relations, which provide relation between finite volume spectrum, and S matrix up to corrections, up to exponential corrections of this form, where M has a cap and R is a size of this of the circle or of the torus, and these corrections are called kind of winding corrections because physically kind of they're associated with loops of virtual particles which wind around the circle, and these particles are massive, and these are exponentially suppressed. And kind of roughly speaking, the way these relations look like, the prototypical example you may think about, if you have a particle, if d is equal to 2, so you have particles on a circle, then when you put particles on a circle for free particles, you have this kind of quantization relation, but these particles scatter, and when you're below the multi-particle threshold, the scattering is purely elastic, so it's characterized by phase shift. So you get this periodicity condition is modified in this form, and well, this is how this Lucier relation looks in 1 + 1 dimensions, and Lucier managed to generalize it to arbitrary number of dimensions, again up to these exponential corrections. Now, kind of there is development, kind of we call it 1 prime because it's morally goes in the same direction. There was a general recently, well, over the last decade, there was a proposal by Sharpe and Hansen, who essentially do provide a generalization of Lucier relations for now, so below 4 particle threshold. So kind of essentially they provide the generalization of these 4 3-particle thresholds, and well, really, what my talk will be about is kind of about our attempt to extend this, and really, first one, I think anybody who tried to read these papers agree that's not an easy read, and actually, somewhat confusingly to us, the answer for Sharpe and Hansen looked very different from what Lucier does, and also procedure looked very different, and even the way the answer was formulated is very different. So kind of what I will tell you is our attempt to understand what's going on there, and I think we have well, probably these papers are correct, although we still don't understand them fully, but we have a kind of picture which I think leads to generalization of this to any number of particles, which can be done in a uniform way, but we're somewhat embarrassed that it's somewhat looks too simple compared to what's going on in these papers, but I'll try to tell you what the picture is. But just for completeness, let me tell you what else is known. So that's known in arbitrary number of dimensions now. Furthermore, in situation somewhat better in 1 + 1 dimensions, namely in 1 + 1 dimensions. Well, it's better because we have simpler series in 1 + 1 dimensions. So first of all, there one can drop the requirement of being below the threshold. Instead, one can think about integrable series. So for massive integrable models, again, up to e to the minus MR corrections, there is asymptotic beta ansatz, which allows to establish this relation for arbitrary n particle states. And it looks pretty much the same for any n, so that's at least one reason to think that it should look also in high dimensions. If such a relation exists, it should look somewhat similar. Well, and finally, also in 1 + 1 dimensions for arbitrary integrable models. So there is thermodynamic beta ansatz.
Maybe you can switch to central board.
Yeah, I'll switch now, but that's not what I'm going to talk about. There is thermodynamic beta ansatz, which actually establishes exact relation between S matrix and finite volume spectrum, again, for integrable models. But this talk will be devoted to this subject. Well, one may be confused because our motivation, as I said, to apply it eventually to lattice data for bullshit scattering of confining string, which is 1 plus 1 dimensional model, but it's massless because we have Goldstone particles. So it looks like even if we understand this step, we're very far from there. Well, if I have time, I can say a few words later about that. But kind of the bottom line is that kind of these winding corrections, especially their sensitivity to UV physics, is less than for in these ABA equations, because roughly speaking, ABA equations, they capture some classical effects, the accumulation of classical phase shifts, and this winding correction is a quantum effect. So there are some 2 pi suppression of winding corrections. So, and there is a way in the context of bullshit scattering for confining strings, there is a way using the TT bar deformation to account leading node winding corrections. So kind of what I'm trying to say here, that actually if we have extension of this technique, which works for in massive theory, it works with exponential precision. Actually, it still will be very useful for analyzing actual data, which Andreas and Mike have, and that will be that I will tell you about. Okay, so let me sketch you now how one approaches this problem. So, well, in general, one starts thinking about some 2-point correlation function of some operator and some fixed external momentum. And for simplicity, although that's completely not necessary for what I'm doing, but for simplicity, I will stick to situation where this momentum is just, well, again, it's of this form. There is only energy. There is no meaning that I'm talking about configuration at rest, which of course, because when working in finite volume, Lorentz symmetry is broken, so that's kind of important, but not very important. And then, kind of if one thinks about any two-point function like that, then by usual argument, one knows that this 2-point function using spectral decomposition can be written as a sum of exponents. So the answer will be with some coefficients. The answer is given by a set of poles. So the goal to find the finite volume spectrum, the goal is to determine the positions of this pole. And so the strategy of what we're doing will be the following. So even though we are after non-perturbative relation between the S matrix and finite volume spectrum, as it often done, we still think about this correlator as being given by a sum of Feynman diagrams, and so we present some arguments, kind of we work at the level of Feynman diagrams and present some arguments which apply to any Feynman diagram, and then assume that property which is shared by any individual Feynman diagram can be then extended to the full theory.
You exclude anti-particles, right? Because
no.
Normally it would be, in normal field theory, it would be E squared minus AN squared. Because of particles, normal Feynman's propagator is P squared minus M squared, right?
And the spectrum would be spectrum of mass. The spectrum would be spectrum of mass, not spectrum of energy. It would be mass, right? What you're talking about. And he's trying to talk it in terms
Well,
of...
he put P spatial equal to 0. So, okay. But it's still E squared minus EN squared.
No. It's just a two-point function. I put here. I'm assuming that you have positive energies. I put here 1 as a sum of all states, and I get
So
this
no,
output.
it's not the standard
Energy square would be still there, right?
No.
Or you can write it as sum of two propagators, and another one would be energy plus here.
It's just
It's relativistic. Yeah.
Misha, it's not time order, it's Weidmann. It's Weidmann
Yeah,
function.
it's just
not
two-point
time
function.
order,
It's-
It's Weidmann.
Yes.
Weidmann.
So it's not T order or not path integral. Because in path integral you automatically get T
No,
order.
it is two. Otherwise, it
Well, you can think about it starting from really, again, if you're on the lattice, you really measure Euclidean two-point function, and then it's a sum of
Doesn't matter the Green's function for local particles.
No, but
E squared minus M squared.
and partial integral it is T order. It is automatically.
Path integral is automatically T order. So since they do path
No.
integral on a lattice, it should be T order.
Well, I think, yeah, maybe you should better think about this just think about this kind of Euclidean two-point function, and what I'm saying that is given by the sum of e to minus n and t. That's kind of really how one determines this. This one we find in
Only non-relativistic thing.
No, that's it in any Euclidean series. That's how lattice simulations are being done, right? That's one measures two-point functions and it extracts from decay. In Euclidean, the two-point functions decay.
Okay, Green's function for let's say free particle, non-interactive.
Yeah.
Can you calculate T product of phi of 0, phi of x?
Yes.
On a lattice or analytically or whatever
Well,
you want.
Euclidean Green's function like this, it's exponentially decaying, right? As a function.
No. Euclidean T ordered, let's say take a free field.
No, Euclidean there is no order. Euclidean is automatically the sum.
Automatically free ordered.
T ordered and Euclidean two-point function
P
is-
squared minus M squared.
No,
Because it's the Green function.
but in the function of t, it's exponentially decaying, right?
Okay.
So there is only decaying exponent there.
This is basic quantum mechanics. Doesn't matter if it's relative
It's
state
near
or
the
not.
pole.
No, it's not.
You just insert intermediate states.
Yes.
It's Euclidean time evolution, nothing more.
Right.
But the Euclidean time evolution could be in a relativistic theory as well, right?
Absolutely.
Yes.
Yeah, and what would be then kind of analog of?
No, but that's the basics of how lattice simulations are done, right? So one looks at two-point function, it's exponentially decaying as a function of time, and these decaying exponents, they give the finite volume spectrum, right?
Let's just move on.
Okay. So as I said, so we think about this as a sum of Feynman diagrams, and the what we're trying to do, because we're trying to we're looking at individual Feynman graphs, and each Feynman graph, well, it's of the form. Yeah, so first of all, because we are on the lattice, so the integration over in the propagators, you have integration over spatial momenta, which is really replaced by the sum over discrete momenta. Ki is 2p ni over L. But then by doing Poisson resummation, one can always replace this by usual integral with the sum over images. Okay, and then the general Feynman graph, which one gets when one will be calculating this two-point function, this Feynman graph will be of the form of the usual form, dd ki, then there is a product of some propagators denominator. There will be some numerator here coming from interactions, but then there will be this Poisson summations appearing upstairs. And so our strategy now is very simple in trying to extract non-exponentially small piece. What we'll try to do, we'll try to look at each individual integral like that, and we'll try to deform the contour integration in the complex domain in such a way that this exponent will become, well, we will be decreasing, right? So we want to get, because we want to drop things, and sorry, this L is the same as R on the form. So we're trying to get a result which is exponentially small. So, but there can be, as usual, there could be abstraction for doing that, because there are these singularities of the propagators which appear here, so to this abstraction, it's determined by this abstraction is determined by the realization of Landau equations, which what we call finite volume Landau equations, namely. So as usual, there is some subset of propagators. One gets assigns to them some positive Schwinger parameters, and there is some subset of propagators which should be 0. And then there is a second condition, which is this form so far, which holds for each loop momenta. And the only difference which arises in the finite volume is that there is this additional term which tells us that kind of these conditions ensure that we shift the contour in such a direction that to avoid singularities of the propagators. But this term ensures that we go in the direction where this exponent is decreasing. Now, let me make a few comments about these Landau equations. So first of all, solutions, just like in the normal Coleman-Norton story, solutions of these Landau equations, they correspond to on-shell diagrams, but the difference is that these on-shell diagrams, because of this term, somewhat not surprisingly, these are all-shell diagrams drawn on a cylinder, on a torus, rather than on infinite volume. So these on-shell diagrams. On a torus. And second comment is that unlike, again, normal Landau equations, which have solutions only into some exceptional kinematics, so these equations have, they generically have a solution. And the reason is that because there is additional parameter which we have. The number of equations is the same, but now there is additional parameter beta which we introduced. And so basically for whether there is solution or not, it depends on the it depends on the value of the energy. So that means the role of these Landau equations here is somewhat different. It's not to tell us when there are certain singularities, but to tell us which kind of subset of diagrams we should look for to determine the finite volume dependence. So essentially, it tells us that something which expected, that this subset of diagrams where we should look for is sounds like this, where in the blob I can drop the this finite volume exponential factors, because there I'm not meeting abstractions, but in here I keep L dependence, and kind of whether there is a solution of Landau equations or not. So depending on my energy, if energy, say, above the 2-particle threshold, but below the 3-particle thresholds, there will be abstractions and they appear here, and I can ignore the 3-particle lines, and etc. So as I increase energy, I have more and more topologies which arise. So that's the main role of these Landau equations. Well, kind of they will play yet another role. I'll say in a moment, but there is, well, because of something which we're confused for a while, because eventually we're interested in applying this to massless particles, and we know that when particles becoming massless, one gets additional power contributions. So the expectation was, well, that should be from. So here I should emphasize these equations. They determine abstraction which is present right away on the real when you start in the real plane of integration. Of course, if one goes deeper in the complex domain, there can be further abstractions, which one needs to take into account if one wants to calculate exponentially small corrections. And the form of the equations will be somewhat different here, because here we made use of the fact that we're on a real plane. But there is in principle analogous derivation, which probably one can make. But kind of the confusion which we had for a while is where binding corrections appear. Power law suppressed binding correction, how do they appear? So it looks like there should be some additional solutions of these equations which appear with series massless. And indeed there are, but kind of they're somewhat funny. So namely, the simplest binding correction would be, for instance, associated with this kind of integral, where this particle is massless, so it's integral dd minus k 1 over k squared. Of course, this kind of integral, it is 0 in dimensional regularization, because there is no scale here. But now if I have factor like this, here I get binding corrections. And so these are exactly binding corrections which become power law. So in the massless case, which correspond to solutions of these Landau equations with beta equal to 0. So it's a conventional Landau equations, but the solution is just trivial one, is k equal to 0. So it's a little bit confusing on shell diagram. It's kind of massless particle of 0k and 0 energy and 0 momentum. So that's a little bit degenerate case. But anyway, that's kind of cross checks that we see how usual binding corrections, how they become power law in this limit. So this is the first step, but of course the second step, now when we identified possible abstractions, now we need to do exercise in multidimensional complex analysis. Namely, we should say, so whenever we have integrals like that, what happens when one picks up those abstractions? And Igor tells me that there is 1 minute. I have 1 minute left, but so at least, well, for 2-particle integrals, it can be done rather straightforwardly. And well, in 1 + 1 dimensions, it's kind of trivial because that abstraction is just a residue. So one reproduces, of course, ABA. In higher dimensions, it's monotrivial because it's now really the multidimensional complex analysis. But at the end of the day, one gets that this abstraction is given by some complex integral over kind of complexified phase space. So no, for instance, yeah, let's say the simplest non-trivial example would be consider two particles, meaning that loop like this at d equals 3. In this case, the phase space is parameterized by one momentum, some space, one special momentum of some particle at fixed center of mass energy, and complexified phase space looks kind of roughly like this. So the integral which one gets, it's have this form. This is a real phase space, but the actual integration contour, it goes something like this. And actually, the most natural place to put it, there is this solution of Landau equation which corresponds to saddle point of this contour. Not surprisingly, because it describes particles like propagating along the real trajectories. And somewhat confusingly, this integral, this natural contour is complex. But the point is that we are trying to, again, to calculate things with exponential precision. So really, all the physics depends only on the behavior of this contour in the vicinity of the real axis. And here there are lots of tricks and where kind of lots of stuff which is being done in Lusher, which looks arbitrary, but actually it corresponds to essentially to choice of this contour. So essentially what Lusher does corresponds to drawing this contour like this, expanded in some basis of functions on the real phase space, and then when there are still some Paolo tail which comes from extension of this contour in the complex plane. But if you have your expression for the function here, it's a technical exercise, but it can be done. And as far as we can tell, for three particles now, it's a more complicated integral, and we are not done yet, but at least at the moment, unless we're missing something, it looks like the story is really the same. So it's always the same kind of exercise in the complex analysis which one needs to do, namely to carefully pick up this singularity and then afterwards kind of resum this set of diagrams after this is being calculated and get Bethe-Salpeter kind of equation, which what Lusher equation is. So yeah, let me stop here. Okay.
Sergei, I have a comment and a question.
Yeah.
So the comment is, I didn't understand your analogy at the beginning, meaning that if I have to think about the S matrix, I would say that we know analytic function that are analytic S matrix for 1 + 1 dimensional integrable models, but we have no idea about higher dimensional amplitudes. How is the analytic structure when you consider multi-particle processes? So that already confused me a little bit. So why do you think that it's simple to generalize the Lusher formula to higher dimensions for any number of particles?
No, I'm not saying it's simple, but I expect the realization should be there.
There is an infinite gap of complication between the two.
No, but the complication which you said is that it just says that there is a S matrix itself more complicated in higher dimensions, but there is no reason to think, a priori at least, that the relation between finite volume spectrum and S matrix should be more, well, it is more complicated, but...
This comes to my second comment that I saw, which is that if maybe the lattice people can confirm this, that the way people explain now the Lusher form is not using the initial argument of Lusher, but now there is a more simple formalism based on the Bethe-Salpeter equation. And I think that's the formula used by Sharp and Max Hunt and Raul Briseno and so on. And from what I understood, I thought that it's complicated because you have a lot of discontinuous contribution. You go, for instance, to 2 to 3 processes where you're like a particle, it's the usual unitary analysis where you
well, there is a complication which is kind of being done because there is a mixture, kind of, if one thinks about 3 particles, for instance, there is a mixture of 2 particles kernels and 3 particle kernels. There is a complication at that level, but yeah, to be honest, we didn't finish sorting out this, but well, in applications to to see the strings at least, we have a way, there is a trick, this TT bar trick allows us to get rid of completely of two particle scatterings and to be in situations when there is just three particle case. And even there, kind of what we're getting looks simpler than what what Sharpe has. For instance, Sharpe equations are not written manifestly in terms of on-shell quantities, although they kind of argue that they're on-shell, but it's not obvious. But even more confusingly, like Lucier equation is naturally written like some equation on the physical phase space. But Sharpe equations for three particle states are written like equations defined on the, like some quantities which define the kk momenta, 2 pi n over r, which is very strange to me, because well, what this free momenta has to do with in the interacting theory, and at least in this way of thinking about it, one always gets equation on just n particle phase space, so which looks.
I thought the analog, how the analog of Lucier term would be a sphere times, like just no, not on a torus, but on a sphere.
No, the Lucier, well, there are several probably Lucier formulas, but the one...
Yeah, no, but just in 1 + 1D, it measures central charge.
No, it's a different Lucier. You're referring to Casimir energy. These are about scattering.
Scattering.
Yeah, that's...
Yeah, that was Marina.
Marina.
Yeah, so maybe just a quick comment. I don't understand whether this it take into account power like L dependence. I think this might be the difference between their three-body derivation and yours, because they don't assume that it's exponentially suppressed, but you also have intermediate three-particle states that can have power law corrections. So it doesn't only come. So the power law corrections don't only come from on-shell, but also from long-distance intermediate states.
Well, that's in the case when there are massless particles. No, but I'm here talking really. No, I'm talking about the same setup as they do. I'm talking about really that discussion was about massive case when all winding corrections they're exponential. So the comment which I had about power law was that for confining strings we really care about massless theory. Where there are additional, where these exponential corrections are not exponential, but power law. But there we have a separate trick how to deal separately with these winding corrections, and that's why it's still good enough to first understand this version of the question. Basically, to talk about corrections associated with real scattering rather than with these virtual corrections, which are winding corrections. But
so you don't assume that there is no power law.
Huh?
You do take into account also power law corrections for this intermediate.
Well, that's the goal here. The goal here is in massive theory to pick up all power law corrections. And that's why that was our logic. So we start with these integrals. We just expect all Feynman integrals and deform them in the region where they're exponentially small, and drop and pick up abstractions which correspond to, which prevent us from doing that deformation. That's really the strategy here.
Okay, well, maybe we should take a break and continue.